Hello everyone, it's Mr. Wolfe here, and in this video I am going to be introducing proportional reasoning. Alright, so let's look at just an example problem. A crane is lowering a large beam to the ground. The large beam suddenly starts to move much faster than before, and you realize the acceleration has doubled. So you don't have to draw this out, but I think it could always be helpful. Here's our crane, here's the beam, and we know that it's increasing speed, so I'm going to draw kind of my motion map right here, showing that it's increasing speed. So that's my situation. All right. Now, when it comes to proportional reasoning, we want to kind of see, all right, we know the acceleration is increasing, but how are the other variables changing, and specifically by what amounts? So let's just focus on our first section right here. What other variable must have changed to cause acceleration to be different? So what I'm going to do is, there's really only one equation we're going to be working with in this unit for proportional reasoning, and that's F net equals ma. So I'm going to draw that right here, F net equals ma. And the best way to figure out what other variable is changing besides acceleration, and we know acceleration is increasing, is I want to look at what other variable is the same. So one thing I'm noticing is that in this case, it's the same beam that is moving, right? And so just by traveling faster, the mass didn't change at all. So my mass is staying the same. So if my mass is staying the same, acceleration is going up, well then that means my F net must be that other variable that's changing, right? Now, we also know that since F net and acceleration are directly related, and that they're on opposite sides of the equation that shows that they're directly related, we do know that my net force should be increasing in this scenario. So not only do we know that it's increasing, but by what factor is it increasing by? So it is important that we show our work here, even though our original proportional reasoning problems are not super complicated. But what we're going to want to do is the one-to-one method. All right? And this is this idea that we're going to assume that everything, since we don't know any numbers up here, is just going to be a 1. So these ones that I'm putting in for acceleration, mass, and net force, right, they're just kind of like placeholders. And we're putting in 1s because those are the simplest numbers that we possibly could put in. Right? 1 times 1 equals 1. But now that things are changing, we're going to change our numbers accordingly compared to these ones. So what I mean by that is that if my acceleration is doubled, well, what's double of 1? Well, that's just 2. So I'm going to plug in 2 for acceleration. If my mass hasn't changed and it was originally 1, that was that arbitrary value we just put in, then I'm going to put in a 1. And then again, I'm trying to see by how much my net force is changing. So 2 times 1 equals 1, super simple math. F net is equal to 2. Now this does not mean it's 2 newtons, it just means that it's 2 times as much as it originally was. This is my factor of change. All right. So if the original force was 600 newtons and the beam has a mass of 500 kilograms, calculate the new value for the variable from A, so over here. So I want to figure out what my actual net force is going to be once it changes by this much. So I'm given 2 numbers, so which one do I use? I'm going to use the one that relates to the variable that I care about. So kilograms is mass, newtons is force, and I'm curious how the net force changes, so I'm going to use 600. This is my original value, and I'm going to multiply that by the factor of change. The factor of change is just this one right here, 2. 2 times as much. Right? So 600 times 2 is going to give me my new value, my new actual value of 1,200 newtons. It's my new net force. All right. And since I do know that my object is accelerating downwards, my net force would also be accelerating downwards because I'm increasing speed. There we go.